Okay, all right. Hello and welcome. It's Friday, so that's good. How are you guys doing? Week four Friday. Next week is week 5, which is, I don't know if it's surprising or if it feels like it's been that long already. I don't know. But we're in the middle of midterm season for the next 5 weeks, and then it's final season. So that's just how it goes. I'm sorry, we still haven't finished grading your exams. I know we're slow, but we're working on it. We'll let you know. And we still have to grade your homework too. I know it's like the grading's. I apologize. We will get there. Okay. Today's topic, we're going to look at multivariate sampling. So we've talked a lot about generating random samples for we've been talking about generating random samples from different distributions. We had inverse CDF, we had rejection sampling, and today we'll talk about generating a sample, a multivariate sample. Okay, and we're just going to touch barely on this for now. We'll look at some very basic examples. We'll look at a multivariate discrete distribution and a bivariate normal distribution. And that's about all we'll say about it for now. And then later on in the course, we can talk about generating more values from more complicated multivariate distributions. Okay? Now, a multivariate distribution is distinct from just generating samples from, say, 2 univariate distributions, right? If you have multiple variables, but they're all independent of each other, you can just generate them independently, right? You can just say, hey, here's, variable 1, we're going to just generate a sample for that. And then we have variable 2, and we're going to just generate a sample for that. Variable 3 follows this distribution and generate a sample for that. And you'll have 3 different variables, and they're all independent of each other. You can just generate them independently as univariate distributions. That's not what we're going to look at today. Sometimes you have a joint distribution, which implies that the distribution for variable 2 depends on the values for variable 1. Right? You got two different variables, and what you get in the second variable depends on what you get in the first variable, and vice versa. So sometimes we need to generate random values from some joint distribution, and we'll just take a look at examples of a couple things. So we'll just start off with kind of this most basic multivariate distribution, right? So we've got 2 random variables, x and y, and these 2 random variables are dichotomous in that they can only generate values 0 or 1. So this is as simple as it can possibly be. X can take on 2 values, 0 and 1. Y can take on values 0 and 1. But they are not independent. Variables x and y are not independent in that if x equals 0, y is much more likely to be 1 than it is to be 0, right? So if x equals 0, y is 0.1 is 1 with probability 0.6, and y is 0 with probability 0.2. Okay? Whereas if x is 1, x and y have probability 0.1 and 0.1. Okay, I mean, y is 0 with 0.1 and y is 1 with 0.1, right? So if x equals 1, it's like flipping a fair coin. You have a 10% probability of being 0 for y, 10% probability for being 1 for y. Whereas if x equals 0, and this seems to be the more likely outcome, right? How often is x 0? X is 0 a total of 80% of the time. 80% of the time, then the coin that you flip for y is going to be different. You're going to get 0 and things like that, right? So how can we generate samples from this distribution? Well, there's a few ways we could do it, right? One is we can first generate x. We can generate x to be 0 with probability 0.8 and generate x to be 1 with probability 0.2. we could do that. And then once you have your x, then you can generate y. If x is 0, generate y with probability 0.2, or not 0.2, it would be 0.2 over 8.8, so 0.25, and y equals 1 with probability 0.75, because you have to kind of scale things up. And if x equals 1, generate y equals 0 with probability 0.5, and y equals 1 with probability 0.5. So you could do kind of this two-step generation, okay? But if you have the joint distribution listed out like this, I think it's easier to just map the entire distribution onto the interval 0, 1, okay? And so, because if we add up all of these numbers, 0.2, 0.6, 0.1, and 0.1, they all add up to 1. So we're going to just map every single one of these things, right? We're going to take these values, 0.2, 0.1, 0.6, and 0.1, and we're going to put them on the interval from 0 to 1. Okay, so P00, this would be the probability of x being 0 and y 0. Okay, that's what P sub 00 would be, this probability. That's probability 0.2. And then we're going to have P00 plus P10. Now that I look at this, it looks like it says poo, but it's P00 plus P10. When we add these two numbers up, we've got 0.2 and 0.1. They add up to 0.3, okay? We've got P00 plus P10 and P01, okay? And so this is, I'm just adding these up in a slightly arbitrary way where you're just going down the columns, and I'm just going down the columns because that's how R adds up its numbers. We're adding up down the columns. We've got 0.2 plus 0.1 plus 0.6, that adds up to 0.9, and then finally if we add up all four numbers together, they add up to 1.0. And so these will kind of serve as our boundaries. And what we're going to do is we're going to generate a value, random uniform value, on the interval 0 to 1. And we're going to say if u ends up between 0 and this first boundary, 0.2, then give me the value 0, 0. Okay, and so we can see that that's going to happen with probability 0.2. If u ends up being between 0.2 and 0.3, between f1, 0.2, and f2, 0.3. So if u ends up being between 0.2 and 0.3, that's going to happen with probability 10%, 0.1. Generate the combination 1, 0 for x and y. And we can see that lines up with this, x being 1 and y equals 0 with probability 0.1. And we just keep going. If the u that we end up getting is between 0.3 and 0.9, we can see that's going to happen with probability 0.6. If it ends up being between 0.3 and 0.9, the values we're going to generate will be 0, 1. X is 0, y is 1. And then lastly, if we get a value between greater than 0.9, so between 0.9 and 1, we'll generate our last values. X is 1 and y is 1. Okay, and so we can kind of generate our values rather than having to do this two-step operation, doing from x first then y, or y first then x. We can generate both x and y together simultaneously by mapping it on the interval 0 to 1. Okay. Does that kind of make sense? We can extend this into anything that's just more complicated, okay? So here, slightly more complicated, x and y, we still have this bivariate distribution. X and y are both discrete. X can take on the values 1, 2, 3, 4. Y can take on the values 1, 2, 3, 4. And so now we have 16 values. If you add up all 16 values, all values add up to 1.0, okay? And so I just kind of made up all of these numbers, and so all of these will add up to 1.0. And again, we could try to generate things in a two-step way, but I'm going to just say, hey, let's take all of these values, because all 16 of these values, if you add them up, they add up to 1. Let's take all of these things and map them onto the interval from 0 to 1. And so to kind of create all of the boundaries, and we're going to have 16 of them now, we're going to just add up down the columns. So if you get, so the first column, first value, P11 is 0.02. And then if we look at the next two values, first two values, 0.02 and 0.03, they add up to 0.05. 02, 03, 04, 2, 3, and 4 add up to 9%. And so on and so forth. We would keep going down the columns until we get to the 15th value where I'm adding up this whole column, this whole column, this whole column, 12, 13, 14, 15. I've added everything up to this value. So everything, I think you can actually highlight the, okay, never mind. Something happened. Okay, so if I add up all of these values, basically, that would add up to 0.9. And then lastly, if I add up the last value, probability of 4, I would get 1.0. Okay, so again, we've got now a distribution and a mapping going from 0 to 1. Okay, how could we implement this? All right, so same idea here. Now I just have a lot more boundaries, and sorry, this should say f sub 14 and f sub 15 to 1, and these would correspond to the values. How could we implement this into our code? So here I've just copied the values from our matrix, 2%, 3%, 4%, 1%, okay, down the column. Okay, so now we would have all 16 values there. And so to kind of fill this out, I just said make a matrix. I entered them and I said fill them out by row. I've got 4 rows. And then what do? I'm going to turn this into a vector. When I turn this into a vector, R fills out the vectors column-wise, right? So it's going to go 2%, 3%, 4%, 1%, then 6, then 4, then 20, 10, then 3%, 2%, 10%, 5%, so on and so forth. It's going to fill up the whole vector down the columns. And I use the function cumulative sum to add up these values. So the first value I get is 2%, 0.02. The next value is the sum of the first 2 values, 2% and 3% to get 5%. And then the next value, 9%, 2%, 3%, and 4% gives me 9%. If I add on the 4th value of 0.01, I get 10%. Okay? And so we could see this vector, this 02, 05, 09, 10%, so on and so forth, aligns with basically the column of values that I produced here. Okay? Although I just skipped a few as far as this slide goes, we could see that these values would align down the column until we get to the end, 90% and 100%. Is that okay? Do we see that? Okay, so then what do we want to do? We want to use this to then generate values. Okay, how can we use this to generate values? So here is that vector of cumulative probabilities. Okay. And then I'm going to create a vector to kind of show us what the corresponding x value and what the corresponding y value will be, right? So if this is our matrix, we take on x is 1 and y is 1 with probability of 2%. And then if I take the next 2 values, 2% and 3%, for this cell, x is 2 and y is 1, okay? Now, I was able to kind of create these labels kind of taking advantage of R's repeat function. So I can say repeat the values 1 through 4, 1, 2, 3, 4, repeat that 4 times. And so x becomes 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And then over here, I say repeat the values 1 through 4, but for the y values, this first column is all 1s, 1, 1, 1, 1, then 2, 2, 2, 2, then 3, 3, 3, 3, and we're going to say repeat each value 4 times. So y becomes 1, 1, 1, 1, then we have 2, 2, 2, 2, then 3, 3, 3, 3, and 4, 4, 4, 4, okay? And it adds on the decimal places just so everything's kind of consistent in the column. Okay. Is this good? And then we generate, let's say we generate a random value u. Okay, and so just for example, let's say the u I get is 0.01. Okay, well, if u ends up being 0.01, according to our rules way back here, we said if u ends up between 0 and the first boundary, which was 2%, we want to generate the value 1, 1. And if u ends up being between the first and the second boundary, first boundary is 2%, next boundary is 5%. If u ends up being between there, we want to generate 2, 1. So if u is 1%, it's below the first boundary, we want to generate the values 1 and 1. So we're going to ask which u, okay, we're going to look at this vector cumulative probability, and we're going to say which of these is true. U is less than which cumulative probability, okay? And it's going to be true for all of them. U being 0.01, U less than cumulative probability being this vector of 16 values, we're going to get 16 trues, okay? And we want to select the minimum of those, okay? So it's going to say it's true for all values, 1, 2, 3, 4, 5, up to 16. What's the smallest? The smallest one is 1. Okay, so our position is going to be position 1. And we say, okay, what is the x value that corresponds to position 1? That's 1. What is the y value that corresponds to position 1? Also 1. Okay, and this is going to be, that's going to be the combination of x and y that we get. Okay, let's try another u value. Let's say u ends up being 3%, 0.03, okay? 0.03 falls in between 0.02 and 0.05, okay? And we said if it falls between this, so our first boundary was 2%. If it falls between the next set of boundaries, 2% and 3%, okay? Which is what we have here, u is 0.03. And that's between 2 and 5, it falls between these two things, then what we need to get is we need to get x to be 2. So kind of following this along, we need x to be 2 and y to be 1. So looking at this, again, we ask which value of u, where is it true where u is less than the cumulative probability, okay? The first value is false, right? Is 0.02, is u less than 0.02? That's false. Is u less than 0.05? That's true. So we're going to get, this part is false, true, 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 which becomes 2 through, the values 2 through 16, and we're going to take the minimum. So the smallest value where this becomes true is 2. So our position is going to be 2. So we're at position 2. We say, what is the x value that corresponds to position 2? The x value that corresponds to position 2 is 2. What is the y value that corresponds to position 2? The y value at position 2 is 1. Okay, and so that's going to be the value that we get. Okay. And so we can just kind of do this with kind of any arbitrary thing. What if we get a generated value and u is 0.89? Okay, 0.89 falls in between 0.8 and 0.9. 0.89 is somewhere in between here. And so we want x to be 3 and y to be 4. And again, we just ask, what's the smallest value where this becomes true, where u is less than the boundaries that we've established? The smallest value where it's true is the 15th value. So we go to the 15th position, and we ask, what is x in the 15th position? X in the 15th position is 3. What is y in the 15th position? Y in the 15th position is 4. And so we could generate our values this way. And so here, I just wrote some code to say, hey, let's do this 10,000 times. Okay, so I'm going to say generate 10,000 random values of u. Okay, and based on that, okay, I'm going to apply this function. Give me the minimum value where u is less than the cumulative probability. And then, and then I run the apply function on u, okay? So I run the apply function on u, and then we subset x to be the position values and y to be the position values to all of these positions. And so that will give me x and y. It's going to generate x and y. Okay, and so I can create a data frame of all of these values, x and y, and just for fun, I can keep all of the u values that are generated, and I can just create a kind of a plot here, okay? And we can see This corner ends up being the lightest color. And this is a little bit, it's hard to read. This is, the X ends up on the horizontal and the Y ends up on the vertical axis, okay? And so this, you have to kind of imagine this being filled out. So it's positioned where 0.02, although it's in the top left corner here, basically we're taking this matrix and we're kind of rotating it on the side because this corresponds to the X and this corresponds to the Y. So take this thing and then rotate it, okay? So that 0.2, 0.3, 0.4, 0.01 ends up across the bottom row, and then 0.2, 0.6, 0.03, 0.05 ends up vertical on the left. So take that matrix and rotate it around, and this is what we have here. 0.02, 0.03, 0.04, 0.01, okay? And then the next row is 0.06, 0.04, 0.2, and 0.1 is what we have here. 0.06, 0.2, and 0.1 here. So again, this is a rotation of this thing. Just because this matrix, the way it's presented is X goes down across the side 1, 2, 3, 4, and Y goes across 1, 2, 3, 4. And we're just basically taking this and rotating it. And that's what we have here. Okay, let me give you your first view quiz answer for today. Today's first view quiz answer is the letter C. C as in cat. C as in cat. Okay, that was the discrete case. Let's take a look at a continuous example. And here we're going to first we're going to start off with generating random normal values. Okay? Now, this is a little bit silly because we have a function already on the computer that is able to generate random normal values, and we're very comfortable using it. We just use our norm, and it produces random normal values. And our norm uses the inverse CDF method for the normal distribution, and it's technically an approximation of the normal CDF function, but it's accurate up to 16 decimal places, and we say, well, that's good enough for me. This, we can use a little bit of creativity here to generate values from the normal distribution from a pair of two independent uniform values, okay? So we're going to take two random uniform values and we're going to transform them using what's known as the Box-Mueller transform into a pair of independent standard normal random variables. And so the idea here is we are going to convert from Cartesian xy coordinates into polar coordinates, radius and angle. Okay? And again, x and y that we're going to generate, these are standard normal random variables, and we're going to just treat them as independent. Okay, so we're going to say the joint distribution of x and y is the product of two independent distributions. So we've got the joint distribution of xy is the product of f of x and the product of fy. And so here I've got the PDF of the standard normal, 1 over root 2 pi e to the negative x squared over 2, times the PDF of the standard normal, this time for y. And therefore when I combine these, I get 1 over 2 pi e to the negative x squared plus y squared over 2. If we want to go from Cartesian to polar coordinates, if you guys remember all of this stuff from back in the day, x is r cosine theta and y is r sine theta. And so we will say we're going to go from f of xy to f of r theta. And it might be a while since you remember this, but when you do a change of variables, okay, you'd say f of r theta, okay, is going to be f of xy, and then we have to, kind of move these dx, dy, and the dr, d theta terms around. And what is this? dx, dy over dr, d theta. We get the partials of xy over the partials of r theta. This is the Jacobian matrix, which I don't know if I'm bringing up bad memories of 32, what is it, A and B? I don't know. But anyway, good times, right? So we say, okay, well, what is dx dr? Okay, and dx dr, so x being r cosine theta, so that just becomes r cosine theta, okay? What is dx d theta? Okay, so we say r cosine theta, what's the derivative of that with respect to theta? We get negative r sine theta. dy dr, so y being r sine theta, we get sine theta. And then r sine theta with what's dy d theta, we get r cosine theta. Then we take the determinant of this, so we have cosine theta times r cosine theta, so we have r cosine theta, r cosine squared theta, or however we read this, okay? And then we multiply these two things together, we take the difference, but it's negative, so it adds up, and we get, so now we get this identity, r cosine squared theta plus r sine squared theta, and these two things add up to 1, all right? So we can factor that out, right? Again, so this just becomes r. Is this okay? We recall all of this, dusting off the cogs in our brain? Or maybe you remember all of this anyway. So, okay, so we have r here. We also have the identity, x squared plus y squared is r squared, okay, as far as the Cartesian to polar relationship. So, if you go back here, right, so what we have f of xy is 1 over 2 pi e to the negative x squared plus y squared. And if we're going to change it into this, we're going to have f of xy times the Jacobian, which we've established is just r, okay? And so when we do this, this is the function in terms of r and theta is f of xy times r, because that's what this part, the Jacobian, evaluated to. And then here, we had e to the negative x squared plus y squared. X squared plus y squared is r squared. So we got 1 over 2 pi e to the negative r squared over 2 times r, okay? And so we say, okay, well, what if we want to change the variable again? Okay, so we're going to have, for r greater than or equal to 0, and theta on the interval 0 to 2 pi, okay, so just one full circle here. Okay, we can say, all right, this is, we have this function, 1 over 2 pi e to the negative r squared 2 r dr theta, okay, and we're going to just switch from r theta to r squared theta, okay, and so dr squared is 2r dr, okay. And so we can replace this part, r dr, with 1/2 of dr squared. Okay, so all of this, all together, we can go from f of r theta dr d theta, becomes f of r squared theta dr squared d theta, okay? And this part, 1 over 2 pi e to the negative r squared times r dr d theta. This is equivalent to 1 over 2 pi e to the negative r squared. And we replace the r dr with 1/2 dr squared. Okay? And now I have a product of two PDFs. One PDF is 1/2, so just rearranging a few terms, one PDF is 1/2 e to the negative r squared over 2 dr squared. And the other PDF is 1 over 2 pi d theta. So here I've got one PDF and another PDF. This corresponds to the uniform distribution from 0 to 2 pi. This is the PDF. 1 over 2 pi is the uniform distribution, is the PDF of the uniform distribution from 0 to 2 pi. Okay? And what is this? 1/2 e to the negative r squared over 2. Okay, well, if you just, this says this is the PDF of the exponential distribution, where we say the value r squared itself comes from an exponential distribution, right? So if we just said y, if this was y, it would be 1/2 e to the negative y over 2, that's just y comes from the exponential distribution. But we're saying y is the value r squared, and so r squared, the random variable r squared, comes from the exponential distribution with rate parameter lambda equals 1/2. Okay? And because we factored this into a product of two PDFs, the variables r squared and theta are independent of each other. It's a lot of steps, all right? And this was the genius of Box and Mueller. Was they saw this transformation. Okay, this is not something that I don't think I would have ever come up with. So they saw this and they said, hey, this is a way we can generate values from the random normal distribution. So how do we implement this? Okay, well, one, we're just going to generate from the uniform distribution, we'll generate a value, theta, representing the angle from 0 to 2 pi. And then we will generate a value v from the exponential distribution with rate parameter 1/2. And we say, well, v is equal to the variable r squared, and therefore r is going to be the square root of v. And we can calculate x being r cosine theta and y being r sine theta. And this will give me two values, x and y, coming from the random uniform standard normal distribution. All right, and how do we generate values from the exponential? Well, we can use inverse CDF method to generate values from the exponential distribution. Just generate a uniform value, take the log of it, and that's basically -2 times the log of some uniform value comes from the exponential distribution. Okay, so this is all you do. Generate this, you get this. Now you have two values from the standard normal distribution. I don't know if I did that too quickly. There is a beautiful, where did it go? Okay, so if you go to Wikipedia, there is this very cool diagram, okay, indicating kind of the relationship, all right? So these dots here correspond to generating two values between 0 and 1, right? So we can generate values where x is close to 0 and y ranges anywhere from 0 to 1. And we can generate where x gets bigger, anywhere from 0 to 1. And so this square represents kind of two random uniform values from 0 to 1. Okay, so x is 0 and y is 0. And then we apply the Box-Mueller transform, and we can see, okay, one of these corresponds to the radius, and the other corresponds to the angle theta. And when we do that, the resulting values will have a bivariate normal distribution. So when your first value of x is close to 0, and you take so remember, transformation. So let's take a look at this, right? So we're generating u from the random uniform, okay, and v from the random uniform. So in our case, if we generate a random uniform value here, we take the log of it, and if it's close to 0, the log of something close to 0 is going to be like a big negative number, right? 0 would be negative infinity, and if v ends up being 1, it becomes 0. Okay, so we take the log of this number, and then we multiply by -2, and we take the square root. So values close to 0 corresponds to kind of a long radius, and as those values get closer to 1, they get closer to, the radius gets smaller, okay? So we can see that, all right? And the rate at which it gets smaller, we can see to go from here to here, the amount that the radius changes is little, whereas to go from here to here, the amount that the radius changes is larger, okay? The other value that we're generating from the uniform, we just multiply by 2 pi to represent the angle. And so we can see values over here correspond to an angle of 0, and as we increase the value, we can see it go around in the circle, right? So as I go up, it just kind of spins the thing around, okay? Which is kind of fun to see, right? And so we can see as I move around, okay, as I stay in this region over here, we're getting values where basically x and y, your standard normal values end up being somewhere between 1 and -1, and as we end up over here, we get standard normal values that are, you know, kind of farther and farther out. So, anyway, this is whoever came up with this illustration on Wikipedia, I give major props to them. Okay, CMG Lee, good job. Okay. I think this is so cool. All right, so that's the Box-Mueller transform. Okay, and so we are now able to generate two values from the standard normal distribution. Okay, so these are two independent normal values from the standard normal. Let me go ahead and give you your second view quiz answer. Second view quiz answer is the letter B. B as in bear. B as in bear. B. Okay, so if we wanted to implement this in R, it's very straightforward. I say I want 1,000 points. Give me 1,000 values, random uniform values, and based on that, do 2 times pi times u, and that will give me theta. Okay, now give me 1,000 random uniform values for v. We'll take -2 times the log of v, take the square root, that will give me the radius, then get x to be r cosine theta, give me y to be r sine theta. So this is just exact straightforward copying of these lines and putting them into a code. Okay. All right, and then when you do that, ta-da, now you get a cloud of points, and these represent 2 random uniform 1,000 pairs of standard uniform values generated random. Okay, we can extend this, and for this part, I'm using Professor Tsang's notes. We're gonna take the 2 independent normal variables to create a bivariate normal distribution, okay? And so with a bivariate normal distribution, we're saying that the joint distribution of the 2 variables x1 and x2, there is some covariance between them, okay? So x1 is a normal variable with mean mu1 and variance sigma 1 squared. x2 is a normal variable with mean mu2 and variance sigma 2 squared. And they have some kind of joint distribution, right? The joint distribution of x1 and x2 will have mean mu1 and mu2, and the covariance matrix of x1 and x2, well, we'll have variances sigma 1 squared and sigma 2 squared, but we also have a covariance value, sigma 1, 2. Okay? If they're independent, then sigma 1, 2 is equal to 0, and this would just be able to be reduced into the product of 2 independent normal distributions. But here we're going to say, you know what, there might be some covariance, meaning if x is a big value, then y tends to be a big value. And if x is a small value, then y tends to be a small value. Or perhaps the covariance is negative, and you just have the opposite relationship. If x is big, then y tends to be small. If y tends to be low, or if x is low, then y tends to be large, or whatever it is, okay? And again, your definition of covariance is basically how much x1 and x2, how much they vary together, right? So the expected value of basically, you know, how much is the difference between x1 and mu1 Okay, if that's positive or negative, you know, compare that to the difference between x2 and mu2, and you know what's the expected value there. So that's the covariance. So how do we do this? So we have these properties. We've got the property, the mean, mu1 and mu2. We've got the covariance matrix as such. And what we're going to do is we're going to say, you know what, let's just create some intermediate matrix, some matrix A. And we're going to just say, suppose this is what we have, all right? A is some matrix with terms A11, A21, A12, and A22, right? And if that's the case, okay, we're going to say, let's make Y, okay? Y comes from a bivariate normal distribution. And the mean of Y, if we say Y is equal to the product of A times X, right? So we're going to take our coordinate X, X1 and X2, and we're going to multiply it by matrix A. Okay, well, what is the matrix, what is the mean of Y going to be? Okay, the mean of Y is going to be A times the mean of X, okay? So if Y is defined as A times X, the mean of Y is going to be A times the mean of X. And what is the variance of Y? Okay. Y is going to have variance. We take the variance of X, and it's going to be multiplied basically by A transform. So when you have one variable, right, if you multiply it by a constant, the variance ends up being, you know, A squared times the variance of X, okay? And when it's bivariate, you have something similar, but it's in matrix form, and you don't square the matrix, you multiply by A times the thing times A transpose. So you're going to have A sigma A transpose. Okay, can we use samples from a standard normal distribution, okay, to generate kind of this, with these ideas, to end up generating a valid distribution X, where it's going to have mean, mu, and variance matrix sigma? Okay, well, the answer, yes. We're going to do that right now. And I've got to do it in 6 minutes here. So what we're going to do is we're going to generate values from the standard normal distribution. We're going to just generate some matrix, some value z. Z comes IID from the normal distribution. So we just generate a bunch of values for z1 and z2, and they're all independent. Okay, and we're going to just say this again. It's coming from a standard normal distribution. If I end up generate them independently, but I combine them, and I say z is a vector of length 2, this is basically a bivariate distribution, bivariate normal distribution, where the mean matrix is just the vector of zeros, and the sigma matrix is just the identity matrix, okay? And this is equivalent to just taking two independent normal values and combining them. And we're going to say, all right, let X be equal to some vector B plus some matrix A times Z, right? And if that's the case, then X will come from some normal distribution, bivariate normal distribution, and we want to figure out, okay, well, what are the properties, mu X and sigma X? And basically, if this is what's going to be the case, can we figure out what B should be and what A should be so that the resulting distribution has the properties that we want? Okay, we want to say, pick a B so that when I do this, X is equal to B plus A times Z, that the resulting mean is going to end up being mu. Okay, and pick an A, and I guess a B and an A also, so that when I take the variance of this resulting variable, when I do A times the Z, Z's come from the standard normal independently, we're going to get this covariance matrix sigma. All right, well, the B is easy. The B is just mu, right? All right. What is going to be the expected value of X if X is equal to B plus AZ? Okay, well, expected value is going to be B plus the expected value of a times z, right? Expected value of a times z is going to be a times the expected value of z. What's the expected value of z? Expected value of z is 0, right? Our values come from the standard normal. Expected value of z is 0. So the expected value of x is just going to be b. So then, if that's the case, just pick b equal to the matrix, or the vector mu that you want. That's easy. The covariance matrix, tiny bit more complicated, right? We say, well, we've defined x as b plus az. What is the covariance of b plus az? Okay. Well, adding a constant doesn't affect the covariance, so the covariance is just a times z. Okay, what is the covariance of some matrix A times z? Well, you can take that out, and just like pulling out an a squared, you have the matrix version of that. You're going to get a covariance z times a transpose. What is the covariance of z? All right, again, z is the two standard normal independent variables. So the covariance of z is just the identity matrix. So we get AIA transpose, which is AA transpose. Okay? AA transpose. So we want to find some matrix A such that AA transpose is going to be equal to the desired matrix sigma. Right? So does this look familiar? AA transpose equals some matrix sigma. Right. So this is what we call the Cholesky decomposition. Right? So if you have some symmetric positive definite matrix sigma, and in most cases your variance matrix is going to be positive definite. Technically it's positive semi-definite, but for most cases it's positive definite. Okay? And we're going to say, well, if you have a symmetric positive definite matrix, which is the case for most sigma matrices, then we have a unique lower triangular matrix A such that we have this, and this would be the Cholesky decomposition. Okay, so how do we find this lower triangular matrix A? All right, well, we could just type into R Cholesky the matrix, and it gives us the decomposition, and that makes our life easy. But it's also, we can kind of figure this out ourselves. So we can just say, all right, we've got these terms A, we got T11, 0, T2, or T11, T21, and it's a lower triangular matrix, so we have 0 and T22. And we want to pick these values, T11, T21, and T22, such that AA transpose is equal to the sigma matrix that we want. The sigma matrix being this. Okay. So all we do is, this just involves some linear algebra, and I will leave it to you and your free time to go through the notes to kind of verify that this is the case. But basically, you just say, well, if A is this lower triangular matrix, A transpose is this, and we want it to equal to this, you can kind of do all of the multiplication. You're going to have basically 3 different equations and 3 unknowns, and you can solve. Okay? So you have 3 equations, 3 unknowns. You solve them simultaneously. Well, really, you can just solve, some of these you can solve very quickly, and you can figure out what each of these terms need to be. Okay, so if you do this, then you will have the desired properties. And there you have it. Okay, so now we can generate values from some matrix Z coming from the standard normal. Z comes from standard normal, another Z2 comes from the standard normal, and then you figure out what your B and your A matrix needs to be. And if you do that, then the resulting variable X will come from the desired distribution with mean mu and variance sigma. Okay, and then so I've done this in code, right? And we said, let's say we want some matrix sigma with covariance 0.7. Okay, if we do that, here I just use the Cholesky decomposition of the variance matrix sigma instead of trying to figure this out myself. Okay, and we would just kind of generate the values from the normal distribution. And when we do that, we get a bivariate normal distribution where there is covariance between x1 and x2. Okay, even though the original values themselves were generated independently, the resulting joint distribution does exhibit covariance. Okay, that's it. That's it for today. We've got, let me give you your last view quiz answer. Last view quiz answer is the letter E. E as in elephant. E as in elephant. Okay, I'm going to post homework 3, and you'll have a week to do that. Homework 3. I think it's rather straightforward. Of course I think that, but I really do think it is. So we'll end here. Have good luck, you guys, and we'll see you guys on Monday. Have a good weekend.